Part 2 of 4.5, we're actually going to graph rational functions. So the textbook calls this graphing rational functions. We will only be sketching. To truly graph, you need a ton of points to know accurately where the graph is. We're just going to have a rough idea of where the graph is. So to sketch irrational functions, there are kind of 5 features that you want to be mindful of. The first feature is an x-intercept. An x-intercept is found by letting y equal to 0. Then this one, totally optional. You don't really need the y-intercept. It's just kind of a nice thing to find sometimes, but it's totally not necessary. And in class this morning, I was kind of like, maybe I should just leave this out. But the textbook does it, so I'm like, you know what? It's not hard to do. To find a y-intercept, you let x equal to 0 and solve for y. Then vertical asymptotes, super important. You're going to factor the numerator and denominator. You're going to eliminate common factors, and then you're going to let your denominator equal to 0. I should have put in somewhere along here too that if there was a common factor, make sure that you find the whole, right? That should be part of your features. And then horizontal asymptote, we will always use y equals 0. So we are only going to be sketching graphs where the degree of the numerator is less than the denominator. And then to provide a sketch, we are going to divide the excess up into intervals using your critical values. Now your critical values are your vertical asymptotes and your x-intercepts. So I'll just maybe put that in brackets here. So your critical values are your x-intercepts and your asymptotes, but the vertical asymptotes. Okay. Remember, the graph can never cross a vertical asymptote, and it might cross a horizontal asymptote. So don't be afraid if you get a point on your horizontal asymptote. It's okay. All right, so let's do this. So graph the function. Be sure to label all asymptotes, list the domain, and x and y intercepts. So first thing we're going to find is those intercepts. Let's find the x-intercept. So to find the x-intercept, we let y equal to 0. When I let y equal to 0, I end up with 0 equals 5 over x squared minus 9. Now, there's a reason we did chapter 3, which was to solve rational equations. To solve rational equations, you multiply by the lowest common denominator, which is x squared minus 9. Both sides, x squared minus 9. When you multiply that denominator by 0, it goes away, and we're left with 0 equals 5. This is what we call a contradictory statement. We solved and the x went away. There's no x to solve for, and the equation we're left with is contradictory. It's not true. 0 does not equal 5, which means that there is no solution or there is no x-intercept, right? So there's no solution. Actually, maybe I should just put that, no x-intercept, because that makes it clearer for this particular graph. Okay, the next thing we're going to do is we're going to find the y-intercept. Now to find a y-intercept, you're going to let x equal to 0. So you're going to find the value of your function at 0, which would be 5 over 0 squared minus 9, which is negative 5/9. So this graph is going to pass through the point 0 and negative 5/9, but that's super accurate. We might use some feature of that, but you might not have to use that entire y-intercept. So I've listed my x and y-intercepts. Done. The next thing I want to do is look for my asymptotes, and via that, I'll do my domain as well. Now at this point, I should have actually started this question with factor your polynomial. You're always going to start with factoring. So this is equal to 5 over, this is a difference of squares, so it's going to be x minus 3 and x plus 3. So to find my vertical asymptotes, you're going to set your denominator equal to 0. So what would make x minus 3 times x plus 3 equal 0? Well, if x equaled 3 or negative 3. Those are my vertical asymptotes. So I'm going to sketch these on here right now. So actually, oh no, I don't have that in this feature in this. So I'm going to just draw a vertical line as best I can. So this is an asymptote. It's vertical. And the equation of it, so to label my asymptote, this is at x equals negative 3. And then here's my other one, at x equals 3. X equals 3. Now that I've done vertical asymptotes, I'm going to do horizontal asymptotes. Now your answer to this will get very repetitive because we are only going to be graphing graphs that have a horizontal asymptote at y equals 0. And again, these asymptotes are not part of my final graph, right? They are just guides for my final graph. But to label it, I would do y equals 0. Okay, before I go on, because I forgot this morning, don't forget to do your domain. I mean, the domain is super easy. It's the set of x such that x cannot equal negative 3 or 3. Or you could do that in set notation, which I'd prefer not to, but negative infinity to negative 3, negative 3 to 3, and 3 to infinity. Don't forget to answer all the questions. Okay, now here comes the most important part. How do I sketch this? Well, something I want you to get used to doing is thinking about the intervals made up with your x-axis. So in other words, what are things that will break up the x-axis? Those are your x-intercepts and your vertical asymptotes. Those are your most important pieces. So I have a vertical asymptote here at negative 3. It doesn't actually exist, so I'm going to put a round circle here. And you have another vertical asymptote here at 3, and I'm going to put another round circle. There's no x-intercept, so there's nothing else to break up this x-axis. So I have 1, 2, 3 intervals to check x values to solve for y to see if the graph is going to be above the x-axis or below. Now I actually already have a point in here. I already found f at 0, and I found that it was negative. So I know that my graph is going to be below. Now I could put that point on, I don't know, it's something like close to negative a half, right? But what that's going to show me is that my graph is below the x-axis here. Now, you will not cross your asymptote unless you have an x-intercept on it. So this graph is not going to go through this asymptote, meaning this horizontal asymptote is going to force this graph down, and when it goes down, it's going to approach these two side asymptotes. So I don't know if this is actually a relative max, but I'm going to treat it like one because I just want my graph to go towards these asymptotes, because again, I'm not graphing, I am sketching. Okay, so I know that between negative 3 and 3, my graph is always going to be negative, and so it's going to point down and approach my asymptotes towards negative infinity. Now I have to figure out what's going to happen to my graph at this interval. So let's pick a value like negative 4, and in this interval, let's pick a value like x is 4. So I don't actually care what the value is. I care whether it's going to come out positive or negative. So if I go back up to my equation, it's 5 over, and it doesn't matter whether you plug it into the factored form or the non-factored form. Okay, I'm going to plug it into non-factored. So it's 5 over negative 4 squared minus 16. Now when I plug that in, all I care about is the fact that the numerator is positive. 16 minus 9 is positive, so I know that my graph will be positive. It will be above the x-axis from negative 3 down to infinity. So from a graphing perspective, I know it's going to be up here approaching the asymptotes. Well, how do I do that? Well, just literally draw a swoop. Right? Approach your asymptote. There's me approaching that asymptote. There's me approaching that asymptote. Now, when I plug in f is 4, is anything going to change? Well, now I have 4 squared minus 9, which isn't any different. It's still positive divided by positive, so my graph is going to be above. And 90% of the time, your graph is going to do this, where in your different intervals, you're going to just swap. So if it's positive in this interval, it's going to go negative in this interval, and then it's going to go back to positive. There's only a few. Like if I go back up here, I can show you one. Here, this one. So if I look at f of x is equal to 1 over x squared, this graph was up, up. It didn't go below. Versus every other graph, if I look at it, it's below, it's above. Right? It's below, it's above, it's below, it's below, it's above. So most graphs will swap, right? They'll be like below, above, but there is those few that pop up that make me have to always check to make sure I'm not messing up. But you'll kind of, once you do a few, you'll recognize kind of the ones that are definitely going to do this floppy thing, and definitely these ones do. All right, so hopefully that made sense, and if it doesn't, don't worry, we're going to do this over and over again. So I think I have 1, 2, 3 more graphs. Okay, and we're just going to repeat the process we just did. So step number 1, let's factor our polynomial. And we're doing that to look to see if there's any common factors. And we're also doing it to find our vertical asymptotes and our domain. Okay, so this is the function in factored form. Very similar to the last one we did. I've just thrown an x in the numerator, and I want you to see what happens when you do that. So first thing we're going to do is find the x-intercepts. To find the x-intercepts, you're going to set y equal to 0. So I get 0 equals 5x, x over x minus 3 times x plus 3. Okay. To solve, I'm going to multiply by x minus 3 times x plus 3. So I'm going to be left with 0 equals 5x. This time the x didn't go away. So you're going to notice this pattern that if there's an x in the numerator, you're going to end up with an x-intercept, and if there isn't one, then you won't. I'm going through this whole process every time because in 4.6 you have to, okay? To find the x-intercepts, you're solving the rational equation. But here I'm left with 0 equals 5x. So to get x by itself, I'm going to divide by 5, and I end up with x is equal to 0. So now I have an x-intercept at 0, 0. Now guess what? When your x-intercept is 0, 0, what's your y-intercept going to be? Right? Let's solve it. I get g at 0 equals 5 times 0 over 0 squared minus 9, which is 0 over negative 9, which is 0. If your x-intercept is 0, your y-intercept is 0 as well. So we'll plot that point. Okay, the next thing we're going to do is find our vertical asymptotes. Vertical asymptotes are found by setting your domain equal to 0, or actually not your domain, your denominator. So x minus 3 times x plus 3, what's going to make that equal to 0? Same as the last graph when x equals plus or minus 3. So now I'm going to draw those vertical asymptotes. They serve as guides. They're not actually part of the graph. They do not exist. They are invisible lines, but they're matter. So this is x equals negative 3, and then x equals positive 3. Okay, and then my horizontal asymptote, because my degree in my denominator is greater than my numerator, it is going to be at y equals 0. Okay, so I want to think about what is breaking up this x-axis. Which x values do I need to choose? Well, vertical asymptotes and x-intercepts are those critical values. They're the ones that are going to split up your x-axis. So I have one at negative 3. Again, it's a point that doesn't actually exist. Now I have an x-intercept at 0, which does exist. And then I have another asymptote at positive 3, which doesn't exist. This time I have 1, 2, 3, 4 intervals in which I have to check my x values. In other words, by putting this x-intercept on the horizontal asymptote means my graph passes through this asymptote. It goes through the x-axis. So let's check that. Well, what do we have to check? Let's try f at negative 4 in here. Let's go f at negative 1 in here. Let's go f at 1 in here. And let's go f at 4 in here. Okay, so let's find those over here. So f at negative 4. If I'm to plug negative 4 into that equation, I get 5 times negative 4. Again, I'm going to put it into the unfactored. I find it easier. Over negative 4 squared minus 9, which gives me, again, I don't care what it is, it's positive or negative. So this is a negative divided by 16 minus 9 is positive. So it's going to be down here. Now, my guess is 90% of graphs then flop. So I'm guessing it's going to go above, below, above. But let's check. So we're going to plug in negative 1. That gives me 5 times negative 1 over negative 1 squared minus 9, which is a negative divided by a negative, which is positive. Then we try f at 1. F at 1, I'm going to get positive over negative, flops down. I'm going to try f at 4. If I plug in f at 4, 5 times 4 is positive. Over 16 minus 9 is positive, so my graph did go positive. So this one followed it. It flopped. Negative, positive, negative, positive. So what does that mean for my graph? Well, here's my intervals. 1, 2, 3, 4. In the first interval, I'm below the x-axis. Now, in here, I have to go through this point 0, 0, but I'm going to approach positive infinity over here, and I'm going to approach negative infinity over here. Right? And then this last one is up in the upper right corner. And that's all she wrote. All right, next graph. So what I would like you to do is pause the video and try this one on your own. So remember, x-intercepts, y-intercepts. Oh, don't forget to answer all the questions. They wanted domain. Let's do domain up here. Domain is the set of x such that x cannot equal plus or minus 3. Right? Or interval notation. I just always forget to answer all the things. Okay, so x-intercept, y-intercept, vertical asymptote, horizontal asymptote, domain, and sketch. Give her a go. So either you stayed with me because you're not feeling confident yet, or you're coming in to check if you're right. But the first thing we're going to do is find the x-intercept. So we're going to let y equal to 0. So 0 equals 1 over x minus 3. I'm going to multiply both sides by x minus 3. I get 0 equals 1, which means there is no x-intercept. Okay, now I'm going to find the y-intercept. I'm going to find the y-intercept by letting x equal to 0. H at 0 equals 1 over 0 minus 3, which is negative a third. So I could, if I wanted to, like right away, put that point in there, but we don't have to be that specific. Okay, then we find our vertical asymptotes. Vertical asymptotes are found by setting your denominator equal to 0. So what makes x minus 3 equal to 0? When x equals 3. This one only has one vertical asymptote. Okay, then horizontal asymptote is where y equals 0. Trying really hard not to do the sound effect that time. Okay, so now that I have my vertical asymptote and my horizontal asymptote drawn, I'm ready to look for my critical values. So my critical value, there's no x-intercept, there's only this vertical asymptote at x equals 3. And so there's only two intervals, right? Above, below, above, below. So I'm going to check a value like f at 0, because I already did. I know that it's negative. Whoa, sorry about that. Look at me being too quick when I graph that. Good thing I checked, right? So when x equals 0, y equals negative a third, it was down here. So I know that my graph is negative, so I'm going to approach both of these asymptotes. Then I could check something like f at 4. If I plug f at 4 into the equation, it's 1 over 4 minus 3. It's positive over positive, so I know it's positive, which means that my graph is going to be up in this corner. And that's it. So just to give you like some weirdo ones, you know, a weirdo one would be something like y equals 1 over x squared plus 9. This is a weirdo one, definitely looks strange. This is literally it. What I want you to notice with this one is that there's no vertical asymptotes, right? What's going to make x squared plus 9 equal to 0? Nothing. If you want to find your zeros, right, your x-intercepts, if I put y as 0, I'm left with 1 equals 0. There are no x-intercepts. So there's no critical values. There's no vertical asymptotes. There's no x-intercepts. So this graph is either all above or all below. Now again, for the purposes of 4.6, we don't care how high above. We don't care how low below. But, you know, if you do these ones, do find the y-intercept. So if I let x equal to 0, I can get that y-intercept of a ninth, which that's what this point is. So take that y-intercept and then just approach your horizontal asymptote, because you have no vertical asymptotes to approach. And again, the other weird one I showed is like 1 over x squared. So if I go into here, right, because this isn't one that flops, it's both up. And there's lots of reasons for this that I wish I had time to teach. I wish we had done reciprocals as a transformation in chapter 1, but we didn't. So just know that most of them flop, some of them don't. Here's an exception, something where it's 1 over x squared, something when there's no vertical asymptotes, right? Then your graph's either all above or all below. But we have one more example. So, oh, there I go again, domain. So the domain of this graph is the set of x such that x cannot equal 3, right? Or negative infinity to 3 and 3 to infinity. Last graph. Okay, step number 1, factor. So I'm going to factor, the numerator's all good. My denominator is a trinomial, so I'm going to factor it down to 2 binomials. I'm going to put my x, I'm going to put my x. I'm looking for two numbers that multiply to give me -2 and add to give me -1. So -2 plus 1. And hopefully you see this common factor of x minus 2. That simplifies to 1. So x minus 2 divided by x minus 2 is 1. And I am left with just 1 over x plus 1. Okay, so that's what I'm going to graph, 1 over x plus 1. But something's going to happen where this is. There's going to be a hole. So maybe right now, let's start off by doing domain since I keep forgetting it. The domain of this graph would be the set of x such that x cannot equal 2 or -1. But we're going to keep in mind that what I'm actually graphing is k of x is equal to 1 over x plus 1. So I'm going to use the k of x is equal to 1 over x plus 1 to graph, but this domain is important because that's the domain of the original function, which is what I'm actually graphing. And I'm just going to get a hole. So if I want to check the hole right now, right, my hole is going to be when x is equal to 2, right? So I could plug that in. So k at 2 equals 1 over 2 plus 1, which is a third. So I'm going to get a hole at 2 and a third. Okay, so I'm going to keep that in mind for a little bit later, but I'm going to graph k of x is equal to 1 over x plus 1. So the first thing I'm going to do is find the x-intercepts. To find an x-intercept, I'm going to let y equal to 0. So 0 equals 1 over x plus 1. Again, I'm going to multiply both sides by x plus 1. I end up with 0 equals 1, contradictory statement, no x-intercept. Then I'm going to find the y-intercept. To find a y-intercept, I let x equal to 0. So k at 0 equals 1 over 0 plus 1, which is 1 over 1, which is 1. So my y-intercept is 0, 1. So I do have this y-intercept at 0, 1, which I can put on there if I want. Then I'm going to find vertical asymptotes. So again, vertical asymptotes, you're going to look here. You're going to look at the simplified graph. So 1 over the function. So I'm going to go 1 over x plus 1. So I'm going to say x plus 1 cannot equal 0. Sorry, I don't have to put cannot equal. That's domain. To find the vertical asymptotes, it's equal to 0. And I get x equals negative 1. So I'm going to draw my vertical asymptote here at x equals negative 1. X equals negative 1. And then my horizontal asymptote, always, 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 y equals 0. Okay, so now what? Well, now I'm going to sketch my graph. So I'm going to look for my critical values. I had a critical value of a vertical asymptote here at negative 1. And then there was no x-intercept, so I only have 2 intervals to check. I'm going to check something like f at negative 2. If I plug, again, into this new function, I'm going to plug negative 2 into here. I get 1 over negative 2 plus 1. Again, I don't actually care what it is. It is kind of nice. It's negative 1. But what I care about is it's negative. So I know my graph down here is down here. Approach those asymptotes. Then I have to figure out what's going to happen. So it was negative here. I'm guessing it's going to be positive, but let's check. Let's plug in something like f at, I don't know, 2, right? If I plug in 2, what happens? I get a value, but that's going to be the whole. So let's not plug in 2, actually. I was going to try to be tricky. Let's not. Let's just plug in 0. So f at 0, we already said that my function at 0, I guess I should be calling these k at 0s. K at negative 2 and k at 0 is 1, which is positive. So it's up here. We already knew that. So what I'm going to do is I'm going to sketch it. So I'm going to sketch it. Maybe I get to go through that y-intercept, and I'm going to approach this asymptote. Now, I haven't put the fact that there's a hole at all, because actually for 4.6, it's not going to matter. And if you graph this on Desmos, the hole isn't really visible. So I could just label a hole. I could say, hey, clearly there's a hole at 2 and a third. Or I could go to my graph, this isn't the best sketch. Let's go like this. Maybe let's go 2 and a third. Let's put a hole. There. And then I'm going to approach this asymptote. And then I'm going to approach this asymptote. Okay, but I've got this hole here at 2 and a third. And remember, it's a hole in the sense that there is no value. Your graph does not exist at x equals 2. And so there would be this tiny infinitesimal small break there. All right, so hopefully you feel confident with these. I gave you tons of examples in the textbook to try. So these are all ones that you can do. I think in the more practice, I even put some more, but this is a really good sampling. I want you to do these until you feel really confident, finding vertical asymptotes, approaching these vertical asymptotes, horizontal asymptotes. When can you cross it? When can't you? What are the intervals? Where do I check points? And once you feel good about that, you've done enough. And so good luck sketching some rational functions.